Hello, General Chemistry gang. In this video, we are going to go through an example calculation involving a buffer. So that is the topic for this video, is a buffer example. And remember, with buffers, we have a couple of things that we have to have is, we need to have initial concentrations of both the parent and the conjugate. Two, the buffer equilibrium is always in terms of the parent, meaning that parent's on the starting material side. And then three, again, that buffers can keep constant pH as a result of the neutralization reaction. So putting that together in terms of an actual reaction, which was covered in the last video, that if we have a solution of, let's say, acetic acid and sodium acetate, right, this constitutes as a buffer. We have our parent acid, and we have its conjugate base. And to write that then in terms of the equilibrium reaction, we would write it in terms of the parent as being the starting material. And we're just writing this like a normal acid-base equilibria, with that parent acid interacting with water, and then we would have acetate on the product side as well as hydronium on the product side. We have, in this case, right, initial concentrations of both. We have an initial concentration of our acetic acid, and we have an initial concentration of our acetate. So both of these are in there initially, even though when we write this equilibrium reaction, we see acetate on the product side. It's not that it's being formed, in terms of starting with zero of that acetate initially. In this case, we have both of those components. So, if strong base is added to the buffer, that means that the parent acid of the buffer system can neutralize that. So if we were to add hydroxide to this buffer, the acetic acid component of the buffer would neutralize it. And so while we are putting hydroxide directly into solution with this addition of strong base, it never actually affects the pH, because the parent acid, the strongest acid of the buffer, neutralizes it. Not only can we go that direction in neutralization, because we have also an initial concentration of the conjugate base, we also have the ability to neutralize strong acid. So in this case, the conjugate base neutralizes the strong acid addition, or a direct source of H+, right? So So even though we add or maybe is created biologically, strong base within a system or strong acid within a system, if we're in a buffered system, then those strong bases or strong acids are actually neutralized. So long as we have enough moles of each one of the buffer components, right? Remember, that goes back to that idea of buffer capacity, which we talked about in the last video lecture. So now let's get into an example of not only how to calculate the pH of a buffer. We covered the concept of that in the last video, but do an actual example of that now. But then also take it one extra step and see what happens when we start to add something else to it, namely a strong base or a strong acid. So here is our example of a buffer type calculation. So we want to calculate the pH of a buffered solution that is prepared by basically mixing 200 milliliters of 0.8 molar glycolic acid. Glycolic acid has this structure. Glycolic acid also has a Ka equal to 1.32 times 10 to the negative fourth. So we're mixing 200 milliliters of 0.8 molar glycolic acid with 200 milliliters of sodium glycolate. And the structure for that is what we see here, where we have pretty much the same structure as the glycolic acid, but now instead of that hydrogen at the end, or that proton at the far right of the molecule with the CO2H, right, we now have that other metal ion, right, the sodium ion. So that is our question. We want to calculate the pH of a buffered solution. That buffer solution is prepared by mixing 200 milliliters of 0.8 molar glycolic acid with 200 milliliters of 0.4 molar sodium glycolate. So let's get that addition into the question there. So there's our question, and trying to reinforce some methodology would be one, starting with, okay, what do I have initially? And if I look at what I have initially, right, I have initially 200 milliliters of 0.8 molar glycolic acid, and I have 200 milliliters of sodium glycolate. So basically I have a solution that contains these two components. We have the glycolic acid, and we have the sodium glycolate. So here is our parent acid, and we have an initial concentration of that, right? This is what we have initially. And then here, with the sodium glycolate, that is our conjugate base. And so we have an initial concentration of that as well. Both of those together tells us we have a buffer. We can also see that in terms of the actual question that we're calculating the pH of a buffered solution. So sometimes that language is also within the question, which makes it very helpful to realize, okay, that now I know I have an actual buffer. So once we have that recognition of what type of question we're involved with here in terms of a buffer, the second part of the methodology, remember, is what is the equilibrium reaction? And then also, what is our Ka equal to? Remember, for our equilibrium reaction, we want that in terms of the parent, right, as that starting material. So if we put together now our equilibrium reaction, we would be putting it in terms of the parent as the starting material. And then that means we would have our glycolate as on the product side and our hydronium ion. Remember here that the sodium is really just a spectator ion. It's not doing anything in terms of pH. It's just really kind of along for the ride. And so since it doesn't change in terms of making a new bond with another molecule or anything like that, it just is really in solution. It's really inconsequential and really not part of that equilibrium process. We have our equilibrium reaction, and so that is defining what our Ka now is equal to. The Ka here would then be our products, the glycolate, and the hydronium in the numerator, all over our starting parent acid. And that Ka is equal to 1.32 times 10 to the negative fourth. So now that we have our Ka set up, we know the important players. This is where we're now looking towards the ice table to then kind of organize the data for us. We have our concentrations of our parent acid. We have a concentration for our glycolate. And we have a concentration for our hydronium. Now, if we go back to the question itself, we do have, 8 molar glycolic acid. We do have 0.4 molar glycolate, but realize that we're mixing those two solutions. So as a result of that, right, realize that we're mixing 200 milliliters of 0.8 molar glycolic acid with 200 milliliters of 0.4 molar glycolate. What does that mean? That means we have new concentrations initially, right? We don't really have 0.8 molar because we're not in 200 milliliters anymore. We're in a total of 400 milliliters. or 0.4 liters. So we have to do a quick conversion to get these initial molarities from the question into their actual molarities when we actually mix the two solutions. So if I start with my measurement of 0.2 liters, I multiply that by 0.8 molar, and then divide by the new volume of 0.4 liters. And this is really just like an M1V1 equals M2V2 scenario, where I'm just doing really a dilution, so moles is constant, and then I divide by the new volume to get to the new molarity. So I really have 0.4 molar in terms of the glycolic acid. And if I do the same calculation for the glycolate, I'm going to find that I have 0.2 molar. We're really just increasing the volume 2 times, which means that we're really halving or taking 1/2 of that original molarity. So there's just the quick dimensional analysis there to get us into the new concentrations. And it's these new concentrations that we are plugging in to our ice table above. So we have our 0.4 molar for the glycolic acid. We have 0.2 molar for the glycolate. And we don't have anything of the hydronium ion. That's telling us our positive direction of change. So on the product side, we would see increasing value of concentration. On the starting material side, we would see, decreasing concentration. And so we get 0.4 minus X for the glycolic acid, 0.2 plus X for the glycolate, and then X for our hydronium ion. So now that we've figured out the concentrations at equilibrium, we can now go to the fourth step, which is to substitute into Ka. Right, once we have it substituted in Ka, we want to solve for X. Remember, X is equal to the hydronium ion. And then once we have that, we can solve for the pH and answer this question. So going back to our Ka, just to write it again, as far as our products of the equilibrium over our starting material, and so that Ka of 1.32 times 10 to the negative fourth would be equal to 0.2 plus X times X in our numerator over 0.4 minus X in our denominator. So we would then undergo assumptions. Right, we do have a Ka less than 1 times 10 to the negative fourth. Granted, it's actually a little bit greater than 1 times 10 to the negative fourth, but it's right on that cusp or that plateau. So we're right in the ballpark, and we have an initial starting material concentration. So our X's, in terms of those initial concentrations, are going to fall out of the expression. And so that means our Ka, the 1.32 times 10 to the negative fourth, would be equal to 0.2 times X over 0.4. And so now we can simply solve for what X is equal to. Remember, X is equal to that hydronium ion concentration, which is equal to 2.64 times 10 to the negative fourth molar. And then plugging that into our pH, right, taking the negative logarithm of that concentration of hydronium ion, and we get a pH of 3.58. Remember, we're not worried about assumption checks anymore. This is always going to work out for buffered systems, and so that would be our answer. Now that's doing it kind of the normal Ka method, ice table method that we've talked a lot about in chemical equilibrium, as well as in acid-base equilibrium and conjugate acid-conjugate base equilibrium. But realize that now we are in terms of a buffer. So we could use instead the Henderson-Hasselbalch equation, meaning that our pH would be equal to the pKa plus the log of the concentration of my conjugate, in this case the conjugate base, glycolate, over my parent, in this case the parent acid of glycolic acid. So I still have to do some steps, in sense of I still have to figure out those new concentrations that we did when we were filling in the ice table. But once I'm done with that, I can really just now solve for my pH. pKa would be the negative logarithm of the Ka, 1.32 times 10 to the negative fourth. Plus then we take the log of the ratio of the conjugate over the parent, or the ratio of the 0.2 molar over the 0.4 molar. And when we put that together, we actually get a pH which should be and is exactly the same as what we got using the Ka method and the ice table method. Remember, these two processes are very complementary in the same thing, so long, again, as you're talking about buffers, right? So let's put that in red here, only buffers, right? That's the only time we can use the Henderson-Hasselbalch. So that's an example calculation of how we can determine the pH of a buffered solution. Now let's look at a continuation of this example in terms of, okay, what happens if we add, let's say, strong base to this buffer? How do we now figure out the new pH that results? And can we determine whether we're still within the buffer's capacity to keep constant pH? So in this second example, this is really continued from above, right? So we're still kind of using that same set of conditions. So we want to calculate the pH of the buffer or buffered solution from above after we add 30 milliliters of 0.2 molar barium hydroxide. So we want to calculate the pH after we've added 30 milliliters of this barium hydroxide to it. And is the buffer still within its capacity? So two questions. I mean, really, we have to figure out the first one, and then once we know the pH, then we can answer the second one as far as the capacity is concerned. So again, we still have that language of a buffered solution, but now we're doing something new. We're saying, what is the pH after 30 milliliters of 0.2 molar barium hydroxide has been added to it. So this would be that idea of exogenous or added strong base. So with that notion of, okay, we know we have a buffer, but now we know that we're adding strong base to a buffered system. That means it's a mole game, right? The reason why it's a mole game is because of the neutralization reaction that has to occur. So now we really have two things going on. We have the buffer equilibrium, which we talked about above, but now since we're adding strong base, that buffer is going to neutralize that strong base. So we really have a neutralization reaction occurring, which is going to set up a new set of conditions, and then we're going to treat it like a buffer question. So as far as this notion, like first we have to figure out the moles of all materials. B, we then, once we have the moles of all materials, we want to set up the neutralization reaction. And then once we get to part C, once that neutralization reaction is done, we're back into a buffer equilibrium question. So you know, we've recognized that it's a buffer, but we can't just go into the notion of Ka and the ice table because we have this other reaction occurring, namely the neutralization reaction. So that's the real big difference now, is saying that we have two processes going on. So let's start with the mole game, right? That we can figure out moles of hydroxide. We started with 30 milliliters or 0.3 liters. I'm sorry, 0.03 liters. We have 0.2 molar barium hydroxide. So that's allowing for our volume to cancel out and get into terms of moles. And then we would want to look at the formula, right? Because for every 1 mole of barium hydroxide, there's actually 2 moles of hydroxide. So our moles of hydroxide would be equal to 0.012 moles. So there's one mole value. We also have to figure out the other mole values too. So we also need to figure out the moles of our glycolic acid, as well as our moles of the glycolate. So for the glycolic acid, we were in 400 milliliters from that question above, and the solution was 0.4 molar. So we have a value of 0.16 moles of our glycolic acid. And we can do the same calculation for our glycolate, where we had, again, the same volume of 400 milliliters or 0.4 liters, and the concentration of it was 0.2 molar. So we get a value of 0.08 moles of the glycolate. So there are our mole values. This allows us now to set up the neutralization reaction. So this was really part A of that recognition that, okay, I need to figure out moles. And then part B, now I'm looking at the neutralization reaction. So strong base is added to this buffer, so it will be neutralized by the strongest acid component of the buffer. In this case, that would be our parent acid, the glycolic acid. So we need to set up that neutralization reaction for that particular process. So we would write this as just a general one-way reaction, that we have an acid part of the buffer. What do acids do? Well, they like to react with bases. Notice this is a one-way arrow. This is not an equilibrium. And when they react with one another, we would produce glycolate as a product, and then also H2O. And so what we can set up is not an ice table, of course, because we're not talking about equilibrium, but we could at least set up an idea of initial and final. Like, we have an initial set of conditions for this neutralization reaction. Remember, this neutralization reaction is going to go 100% because of the idea that we have something very strong within that, namely the hydroxide is ensuring a strong transition or 100% conversion to products. And so now we just put in our mole values that we have, right? This is like going way back to just general reactions, right, in terms of moles of one thing and moles of another. So we had 0.16 moles of our glycolic acid. We have 0.012 moles of our hydroxide. And we have 0.08 moles of our glycolate. And we don't have any water, at least initially, based off of this specific neutralization reaction. Hopefully remember terms such as limiting reagent, right? The hydroxide has the least amount of moles in terms of those two starting materials, so it's actually going to run out first, and we would end up with 0 moles of that hydroxide. So again, the exogenous strong base is completely neutralized by the buffer components. So that's really kind of our mole value of change, that we would be losing glycolic acid by that mole value of hydroxide, but we would be gaining that mole value in terms of the products of this neutralization reaction. So in terms of the final set of mole values that we have after the reaction is complete, right, we have 0.148 moles for our glycolic acid that's left over. We have no moles of the hydroxide, it's been completely neutralized. We have 0.092 moles of our glycolate, and then we would have 0.012 moles of our water. So in terms of this, we got to say, well, what's now going to affect the pH, right? Our buffer components are going to define our pH. We still have our parent acid, we still have our conjugate base, so we're still talking about a buffered system. Water here is not going to affect pH, right? Even though it's formed, right? Water is very weak, and we have some things in solution that are much stronger than water actually is. We have a parent acid, which is a much stronger acid than water is. We have a conjugate base, which is a much stronger base than water is. And so even though we're forming water, it's really inconsequential to the pH type of calculation. So now that we have our new mole values, we can then basically get to the last piece, which is now looking at the buffered equilibrium. So you have, again, this idea of a choice. You could choose Ka, ice table, or you could use the Henderson Hasselbalch equation. And I'm choosing the Henderson Hasselbalch. Right? Either are valid, right? Whatever you feel more comfortable with. If you feel really comfortable with the ice tables, go ahead, do the ice table and do everything that we've done in the past, following like the example we have above in this lecture. Or like I used in that example earlier, we could just use the Henderson Hasselbalch. So we have to get back into terms of concentration. Right? Whatever method we're using, the ice table Ka method or the Henderson Hasselbalch, we have to get back to our new concentrations that we have. And so we had now a new mole value of our glycolic acid, which is now 0.148 moles. And here's a tricky spot. Notice that our volume has also changed from 0.4 liters to 0.43 liters. So where is that coming from? Well, that's coming from the fact that we had 400 milliliters of the buffer, but then we just added 30 milliliters of this barium hydroxide solution. So here was the original buffer in terms of our 400 milliliters, and then here is our barium hydroxide that we just added to that. So we have to change that volume, right, because that's changing the concentration. So we get 0.344 molar in terms of our glycolic acid. And if we do the same thing now for our glycolate, we had now, as a result of the neutralization reaction, 0.092 moles of the glycolate were in the same volume. So again, that's just that new volume is coming from the 400 and the 30, like we had above. And that is going to equal 0.214 molar. So now that we have those new concentrations, we can plug that directly into our Henderson Hasselbalch expression. So, right, our pH would be equal to our pKa plus the log of the conjugate, the glycolate, over the glycolic acid. And so now we're just plugging in our values, right? pH would be equal to the negative log of our Ka for the pKa That was 1.32 times 10 to the negative fourth. And now we want to add to that the log of the ratio of 0.214 molar for the conjugate base glycolate over 0.344 molar, the parent acid glycolic acid. And when we do that, we get a pH of 3.67. You should get the exact same pH if you chose to use the Ka method and the ice table method. Since the pH has not changed by plus or minus 1 pH unit, right? Remember, we started at a pH of 3.58 that was original, and now we're at 3.67. So that was our original, the 3.58, and now this is 3.67 after strong base addition. Notice that that's, like not even 0.1 pH units. So since the pH has not changed by plus or minus 1 pH unit, we are still within the buffer's capacity. So that is an example of adding strong base to a buffer. So in this lecture, we've gone through an example of a buffer calculation, and we've gone through an example of what happens when something strong, in this case a strong base, is added to a buffer system. Please understand that the example done here is an example of a parent acid conjugate base buffer. Please make sure you try examples of the opposite scenario, meaning instead of a parent acid conjugate base buffer, make sure you can do similar calculations involving a parent base conjugate acid buffer, right? The other side of the coin.